Another connected objects question. This one looks a little bit different. I don't have a hanging mass. I've got two, they happen to be on a level surface, and the one that I'm going to call at the front, we're pulling with an applied force that happens to be on an angle. As you'll see as we work through these, the concepts we worked on previously in forces are going to overlap. So we'll use applied force on an angle within a connected objects question. Otherwise though, it's the same method to solve it. Draw free body diagrams, push them as far as you can go. For this one, I'm going to start with a 2 kilogram object. Free body diagram on that. Normal force upward, gravity downward, friction backward, and the string, so I'm going to call it tension, is pulling it forward. I would call this a boring case. Nothing's happening in the vertical, so the normal is equal to gravity, which is mg, which for 2 kilograms works out to be 19.6. In the horizontal, it is accelerating, so we're going to set up F net equals ma. The forward force is the tension, the backward force is the friction. That's going to be ma. Friction is always mu times Fn. For the boring case, that's going to be mu times mg. We know what mg is from before. When I put in all my numbers, tension minus the 19.6 times the 0.2 number is roughly 4, and that's equal to 2 times A. That's as far as I can take the 2 kilogram object. The Ft is positive. We've got a negative friction force, and that's equal to ma, or 2a in this case. The other object, the 3 kilogram object, is a little bit more complicated. Take a peek at that before I scroll. All right, when I draw a free body diagram of the 3 kilogram object, gravity's pulling it straight down. That's easy, hopefully. Normal force is straight up. On purpose, I'm drawing a little bit shorter. There's friction backwards because it's on a surface with a given coefficient. There's that rope tied to it, so there's tension backwards, so that's different. We have 2 backwards forces. And the forward force is on a 30-degree angle, and it happened to have a value of 30 as well. So 30 newtons on a 30-degree angle. Because there's a coefficient of friction, I have to work through the vertical component. It's not a boring case. Now we have a force acting on a funny angle. I need to take components of that force. We'll need the horizontal component and the vertical component. Vertical component's opposite the angle, so that's going to be related to sine. The horizontal component is adjacent to the angle, that's going to be related to cosine. When I figure out the normal force, I'm going to say that all the up forces must balance the down forces. In this case, we've got 2 upward forces. The normal is up, and 30 sine 30 is up. The only downward force is gravity, which is mg. So my normal force is 3 for the mass multiplied by 9.8. Take away 30 sine 30. You can do that a little bit in your math. We've got roughly 30 minus roughly 15. With a calculator, I'm getting 14.4 as the normal force. Now I'm going to look at the horizontal. Horizontally, it's an F net equals ma situation. There's only one forward force. That's the 30 cos 30. But I've got 2 backward forces, so I'm going to have 2 negatives. The friction is backwards, and the tension is backwards. That's equal to ma. 30 cos 30, I'll crank that out as a number shortly. Friction's mu Fn. Ft I can't do anything with. That's equal to ma. If I put in everything I know now, 30 cos 30, it's almost calculator time. The mu that I made up for this one was 0.3. The normal force, we just figured it out, was 14.4. Take away Ft, I don't know what that is. equals 3a. 30 cos 30, we're going to get a pretty big number out of that. Cos 30 is close to 0.9, so like 26 or 27. Then we take away the friction, the 0.3 of 14. I'm getting on my calculator 21.7 is the number. Ft is a negative, equals 3a.
Ms. Wong, line 104. Ms. Wong, line 104.
I'm going to call that equation 2. Just like we saw before, we're now kind of done the physics part of it. To look for is tension's a positive force on the one and a negative force on the other. From here, I can solve my two equations. The first equation, Ft minus 3.92 equals 2a. My second equation, the number part, was positive 21.7. Ft was negative, and that was equal to 3a. If we set it up right, it's always going to be, we can always solve by elimination by adding our two equations. The Ft's will cancel out. In this case, I've got the 21 number, take away roughly 4. That ends up being 17.7 with some rounding, and that's equal to 5a. Dividing both sides by 5, the acceleration ends up being 3.6.